Hello friends, I welcome you in lecture number 25 on partial derivatives. In this lecture we will discuss this example on method of Lagrange multipliers. We have discussed method of Lagrange multipliers in lecture number 24. So if you have not watched that lecture, I suggest you to watch lecture number 24 to understand the method of Lagrange multipliers. So we just recall that in Lagrange multiplier we are given some function. Suppose here we consider function of xy. So we are given some function of xy which we want to maximize or minimize subject to some condition which we have written in this form. Some function of xy says g equal to 0. Then Lagrange method says that we have to solve the system of equations given by gradient of f equal to lambda times gradient of g with this equation gxy equal to 0. So we have to find out values of xy which satisfy this system of equations. After finding those values of xy, we will find out value of this function f at all these points which we obtain by solving this system, and from that we will decide that at which point function is maximum and at which point function is minimum. So we will decide the points at which function is maximum or minimum subject to this condition by solving this system of equations. So here we have to find the maximum and minimum values of function fxy equal to 3x plus 4y on the circle x square plus y square equal to 1. So here we are given function fxy which we have to maximize and minimize on the circle. Here fxy is 3x plus 4y and the constraint on this x and y, the constraint is x square plus y square equal to 1. This we denote by equation number 1. So from the constraint we consider function g equal to, we can write x square plus y square minus 1. Now we have to solve the system. So for that we consider the system which is given by gradient of function f equal to lambda times gradient of function g, where lambda is called Lagrange multiplier. Here f is function of two variables, therefore gradient of f has two components, del f by del x and del f by del y, and gradient of g has two components, del g by del x, del g by del y, and this we can rewrite as lambda times gx comma lambda times gy. Therefore we obtain these two equations, del f by del x equal to lambda times gx and del f by del y equal to lambda times del g by del y. So we have to find out partial derivatives of f and g with respect to x and y, and we will substitute them in these two equations, and we will solve these two equations together with this constraint equation 1, x square plus y square equal to 1. Now f is 3x plus 4y, therefore del f by del x is 3 and del f by del y is 4. So here del f by del x is 3 and here del f by del y is 4. Now we consider partial derivatives of g with respect to x and y. Del g by del x will be 2x and del g by del y will be 2y. So here we write lambda times 2x and here we have lambda times 2y. So from this I can say that this is equal to, this we rewrite as 3 equal to 2 lambda x and 4 equal to 2 lambda y. Now from this, if lambda is non-zero, we can write this equal to x equal to 3 divided by 2 lambda, and here we can write y equal to 4 divided by 2 lambda, or we can cancel out 2, but we keep this as it is. So here we assume that lambda is non-zero, and from these two you can see that lambda must be non-zero. Suppose lambda is 0, then from this we will get 3 equal to 0, which is not possible. So lambda is always, lambda equal to 0 is not possible. Okay. Here we can write this justification that why lambda is non-zero. So we can give this star, and we can say that lambda is non-zero, and the reason is, if lambda equal to 0, by equation number star we obtain that 3 equal to 0, which is not possible. Therefore lambda is non-zero, and therefore we obtain x and y in terms of lambda by taking this lambda on the left hand side. Here also we consider y equal to 4 divided by 2 lambda. Now we have not used equation number 1. So now we substitute values of x and y in equation number 1. Equation number 1 is x square plus y square equal to 1. So we put values of x and y in equation number 1. Putting values of x and y in 1, we get, so we consider x equal to 3 over 2 lambda square plus y is 4 over 2 lambda. So x square plus y square equal to 1. So this we can rewrite as 9 divided by 4 lambda square plus 16 divided by 4 lambda square equal to 1. Therefore we obtain 9 plus 16 divided by 4 lambda square equal to 1. Therefore 4 times lambda square equal to 25. That gives us lambda square equal to 25 divided by 4. Therefore lambda equal to plus or minus 5 by 2. So there are two possible values for lambda. So using this value of lambda, we will find out values of x and y. X is 3 divided by 2 lambda. X equal to 3 divided by 2 lambda. That is 3 by 2 into 1 by lambda. Lambda is plus or minus 5 by 2. Therefore 1 by lambda is plus or minus 2 by 5. So 2 will cancel out, and we obtain x equal to plus or minus 3 divided by 5. Similarly y equal to 4 divided by 2 lambda, that is we can cancel out 2 here, and we obtain y equal to 2 divided by lambda, that is 2 into 1 by lambda. 1 by lambda is plus or minus 2 by 5. Therefore y equal to plus or minus 4 divided by 5. So therefore the function has extreme values. The function has extreme values at points. The possible points at which function is maximum or minimum are x, y equal to plus or minus 3 by 5, 4 by 5. So these are the points on the circle. We can check whether we have correctly find out these points or not. We can substitute values of x and y in this equation. They must satisfy this equation. So if we take x square plus y square for example, then we can see we will obtain 3 by 5 square plus 4 by 5 square, 3 square that is 9 plus 4 square that is 16 divided by 25, and we obtain 1. So we have obtained correct points on the circle at which function is either maximum or minimum. Now we have to decide that out of these 4 points, at which points function is maximum and at which points function is minimum. By using this Lagrange method, we are able to decide the points which satisfy the given constraint and the function is maximum or minimum at those points. So now we substitute value of those 4 points in this function, and we will have the idea that at which point function is maximum and at which point function is minimum. fxy is 3x plus 4y. So now first we write down that function. Given function is fxy equal to 3x plus 4y. Now the 4 possible points are 3 by 5. Here I have to write plus or minus 4 by 5. So the possible points are 3 by 5, 4 by 5. Both are positive. One is positive, another is negative. Then minus 3 by 5, 4 by 5, and fourth possibility is minus 3 by 5, minus 4 by 5. So you can directly observe that at which point function will be maximum and at which point function will be minimum. Here we have addition of 3x and 4y. So we can see function will be maximum at this point 3 by 5, 4 by 5, and function will be minimum at this point at which both x and y are negative. Or you can calculate the value of function at all these 4 points, and you can decide that function is maximum at this point and function is minimum at this point. But here it is clear that function is maximum at point 3 by 5, 4 by 5. Function has maximum value at point 3 by 5, 4 by 5, and maximum value is equal to value of function at this point f of 3 by 5, 4 by 5. We substitute x equal to 3 by 5, 4 by 5. 3 times x component, that is 3 by 5, plus 4 times y component, that is 4 by 5. Here 5 is LCM, and we have 3 into 3, 9 plus 16, that is 25 divided by 5. So therefore maximum value of function on the circle is 5. Similarly, we can write that fxy has minimum value at point minus 3 by 5, minus 4 by 5, and minimum value is obtained by finding value of function at this point. We substitute x equal to minus 3 by 5, y equal to minus 4 by 5. Function is 3 into x plus 4 into y. So this is equal to, again we can take 5 LCM. Here I have 3 into minus 3, minus 9. So I will have minus 25 divided by 5, that is minus 5. So minimum value of function is minus 5, and it occurs at this point on the circle, and maximum value of function is 5, and it occurs at this point 3 by 5, 4 by 5. And you can check value of function at remaining points also. For example, suppose I calculate value of function at point 3 by 5, minus 4 by 5. then it is going to be 3 into 3 by 5 plus 4 into minus 4 by 5, that is 9 minus 16 divided by 5, that is going to be minus 7 by 5. So this is going to be less than 5, which is maximum value of function, and it is going to be greater than minus 5, which is minimum value of the function. So we can say that function has maximum value at this point and minimum value at this point. Maximum value is 5, minimum value is minus 5. So in this way we can apply method of Lagrange multipliers to decide the maximum and minimum values of given function satisfying given condition. Here function was 3x plus 4y, condition was given by this circle x square plus y square equal to 1. So we have obtained the points on the circle at which function is maximum and point on the circle at which function is minimum. So function is maximum at this point 3 by 5 comma 4 by 5 on the circle, and maximum value is 5. Function is minimum at this point on the circle and minimum value of the function is minus 5 on the circle. So this is all about this session. In this session we have maximize and minimize this function of two variables subject to the condition. So this is all about this session. I hope you like it. Thank you.